Having obtained the expression for Lz as summation I mi Ri square omega, where Ri is the perpendicular distance from the axis of rotation, and we call this quantity the moment of inertia I omega. Let us calculate this quantity I for certain simple and slightly more involved elements. For example, if I have a rod or even a rectangle rotating about the axis here, or this rotating about the axis here, what is the moment of inertia? This is rotating right now, let us say going into the plane or coming out of the plane. So, we can generalize this definition, which we wrote as mi Ri square, as equal to integral some mass dm, which is at a distance r square, and integrated over the entire body. For example, in this case, if I take a small strip here at distance x, the width of this strip is dx, then the I for this would be given as integral sigma, I will define what sigma is in a moment, dx times the width of the rectangle times x square, where x square is the square of the perpendicular distance from the axis of rotation of this mass dm, sigma is mass per unit area, which in this case would be the total mass divided by L times W, where L is the total length of the rectangle. The integration is going to be from x equal to 0 to x equal to L. So, let us do that, and when we do that, I get I is equal to integral dx sigma omega x square 0 to L, where I am talking about this rectangle rotating about one of its side, length L, width W. So, this comes out to be sigma W L cube over 3. Sigma W L is nothing but the mass, so mL square over 3, a result that you are well familiar with. As a second example, let us take a ring of mass m and calculate its moment of inertia about its center. Then if I take any mass dm here, all over the periphery the mass is at the same distance from the axis r, and therefore, I is going to be dm the radius square integral, r is a constant, so it comes out to be m r square, another familiar result. As a third example, let us take a disk, a solid disk of mass m and radius r, and I want to calculate its moment of inertia about an axis passing through its center. What I can do for this is divide the disk into small rings. Of width of radius dr. Then the moment of inertia for the disk, I know if its mass is dm, is going to be dm r square, and if I integrate this, it gives me the moment of inertia for the disk. dm is going to be mass per unit area of the disk, which is m divided by pi r square, times the area of this small section that I have taken, and this is going to be 2 pi r dr times r square integrated from 0 to r. And what I get is this pi cancels, 2 m over r square times r raised to 4 divided by 4, and the result comes out to be mr square by 2. That is the moment of inertia of a solid disk about an axis passing through its center. The result could easily be generalized to a cylinder also, which is this disk elongated along the z axis. Next example, I take the same solid disk, however, now I take the axis as its diameter. So, this diameter is the axis. For calculating a moment of inertia about this, I will take a strip on the disk like this of width dx, so that its mass is going to be m over pi r square dx times this length, which I will call 2 times y, where y is this length. Multiply this by x square and integrate from minus r to r, because this distance is r. What is y? Y is, you can see from this right angle triangle, is going to be equal to square root of r square minus x square, and therefore, the moment of inertia about one of the diameters is going to be integral from minus r to r m over pi r square times 2 y is square root of r square minus x square times x square dx. Let me take x to be equal to r cosine of phi, that gives you dx is equal to r sine of phi d phi with a minus sign in front, and the limits for this are going to be, for minus r is going to be pi, for x equal to r is going to be 0. With this minus sign, the limits change. In any case, I can write this as, let me write it again. I am talking about the moment of inertia about the diameter. I is equal to m over pi r square times 2 the square root of r square minus x square dx. Integral is from minus r to r. I have taken x to be equal to r cosine of phi, and with that this integral changes to pi to 0 with a minus sign in front, m over pi r square times 2 r square minus x square, this will become r sin phi, x square is going to be r square cosine square phi, dx is going to be r sin phi d phi. I have already taken care of minus sign outside, which I can write as this r square cancels, 2 m over pi zero to pi sin square phi cosine square phi d phi, which is equal to 2 m over pi 0 to pi sin square phi cosine square phi d phi, which is equal to m over 2 pi integral 0 to pi sin square 2 phi d phi. Change to variable alpha equals 2 phi, this becomes equal to m over 2 pi 0 to 2 pi sin square alpha d alpha divided by 2. I have forgotten r square somewhere. There was an r square here, so that will remain. There is an r square here, there is an r square here, there is an r square here. So, what we get for the moment of inertia about diameter is mr square over 2 pi integral 0 to 2 pi sin square alpha d alpha over 2, which is equal to mr square over 4 pi integral 0 to 2 pi sin square alpha can be written as 1 minus cosine 2 alpha over 2 d alpha, and this you can see right away is nothing but mr square over 4 pi times pi, which is mr square by 4. A result again you are well familiar with. So, for a disk about its diameter, the moment of inertia is mr square by 4. As last example, let us do a sphere about one of its diameters. For this, what I am going to do is take a cylindrical shell around the diameter, so that the mass of this cylindrical shell is going to be its volume, let us call it dV, times the density, which is going to be m over 4 pi by 3 r cubed. The volume of this cylindrical shell, if I take this to be of radius r and thickness dr, is going to be dV equals 2 pi r dr, and this whole length, let us call it 2y times 2y, where y is this height, which I can write as 4 pi r dr. Y, as we calculated in the previous example, is going to be r square minus r square, and therefore, the mass is 4 pi r dr is square root of r square minus r square times m 3m over 4 pi r cubed. This 4 pi cancels, and therefore, I get as the mass of this sphere as dm equals r dr square root of r square minus r square m over r cubed. This is a cylinder, and therefore, the moment of inertia of the sphere is going to be the perpendicular distance of this is like a ring, is r square times r square root of r square minus r square m over r cubed. Oh, there was a 3 here, times dr. So, this is equal to 3m over r cubed. R varies from 0 to r cube is square root of r square minus r square dr. To evaluate this integral, again I use r is equal to r cosine of phi, so that dr is equal to minus r sine of phi d phi, and limits are going to be from 0 to pi by 2. So, substituting, I am going to get I equals 3m over r cubed integral, let us see this is 0. So, at 0 it is pi by 2 to 0. For r cubed, I get r cubed cosine cubed phi, square root r square minus r square comes out to be r sine phi times minus r sine phi d phi. This r cubed cancels, and I get 3 mr square 0 to pi by 2 cosine cube phi sine square phi d phi. To evaluate this integral, let me write this in a particular way: 3 mr square 0 to pi by 2 cosine phi, cosine square phi will be left, which I will write as 1 minus sine square phi d phi, and let sin phi be equal to z, so that cosine phi d phi is dz, and limits are going to be from 0 to 1, and therefore, the moment of inertia I is going to be 3 mr square 0 to 1 dz z square minus z raised to 4, which is nothing but 3 mr square times 1/3 minus 1/5, which is 2 mr square by 5, and that is the moment of inertia of a sphere about one of its axes. As another example of angular momentum conservation, let us consider a huge platform which can rotate without friction in one particular direction or any direction. And let us take a person of mass m moving on its periphery with a speed v with respect to the platform. Let the radius of the platform be r and let its mass be m. We want to know with what speed would this platform be moving, with what angular speed would this platform be moving. So, again initially if there is no angular momentum, then L should be equal to 0. If the person moves with respect to the platform in this direction with v, the platform starts rotating the other way with omega, so that the net velocity of the person with respect to ground is going to be v minus omega r, and therefore, the angular momentum of the person is going to be m v minus omega r. On the other hand, the angular momentum of the disk in the opposite direction of the platform is going to be m r square by 2 times omega, because this platform is like a disk, and the two should be equal in magnitude because they are opposite in direction, so that the net angular momentum is 0, and therefore, what we get is m v minus omega r times r is the angular momentum should be equal to m r square by 2 omega, which gives me 2 m v is equal to m r square plus 2 m r square omega, or omega equals 2 m v over m r square plus 2 m r square. There is a r here, m v r, which is nothing but v over r divided by 1 plus m over